So when we're trying to describe waves, we need to describe not only their position, but how they move with time. And this turns out to be a little more complicated than it might seem initially. So with a pulse, it's fairly easy to talk about here's a pulse at some point, and then here it is later. And we can describe this with an equation to describe the shape of the pulse, and then we can describe it with an equation that describes the shape of it later. We can sort of time evolve it if we like. But I think it's useful for us to think about it in terms of a snapshot view, which is what I can draw, snapshot view, right? At different times, time 1, time 2. Those are the snapshots that we have, versus the raft view, which would be a position versus time graph. What happens on the raft? So as you're sitting on the raft, you go up and then down, right? If your raft is right here, you're about to be hit by the wave, and then sometime later the wave has passed through, so you have gone up and down. So that gives us the snapshot view versus the raft view, which is at some value of x, and it varies with time. The snapshot view is going to be the picture of the wave as a function of position, when it's high and low at different x positions at a given time. So picture of the wave at a given time versus how the position varies. The raft is sitting at x and how the y position varies with time. And when we change this to a sine wave, this gets even a little bit more complicated. But it's actually easier mathematically to describe. We just have to keep the same information in mind. So this might be at time 1 is our wave if it's traveling to the right, and then we can go like this at time 2, for example. And if it goes on and on, then we can describe it with a sine or a cosine. And so again, this is our snapshot view. And then our position versus time is also going to go up and down. And so what we do is we describe this by saying the y position, this is the snapshot, this is y versus x, right? And this is y versus x, oh, sorry, my x is not in the middle, y versus x at a time later on. There. So we have this it has traveled on. And so what we're looking at is something that is a function of, but y is a function of both x and t, or if you prefer, you'll often see it as f of x of t. But it's really telling you what the height is at any particular position x, like if you're sitting right here, and then if you're at that position, then time later, what happens at that position at a different time. So we can describe this by its amplitude, this a, how high it goes up, sine of now 2 pi over lambda x minus 2 pi times the frequency times time. And so what this does, so you often will see it like this, where we still have that the speed of the wave is given by the frequency times the wavelength. And notice these units work okay because x and lambda all cancel out. They're both in meters. Same thing, frequency and time in seconds. And then this 2 pi gives us this every 2 pi radians, it repeats itself. So when x is equal to some value of the wavelength, we're back to sort of our starting position. And same thing when your time is equal, when you're at 1 period, which would be 1 over the frequency, you're back to 2 pi later. You've kind of, you've gone from here back to this same sort of starting position. And so as we look at this, this equation will give us then, if we say time equals 0, for example, putting in this equation, y of x 0 looks like a sine of 2 pi over lambda x. And so that tells us that at time equals 0, this looks like a sine wave, for example. Or we could say then at a time of 2 seconds later, we could then say our y of x and t equals 2 is a sine of 2 pi over lambda x minus 2 pi times the frequency times 2. And then you just, depends on what the frequency is as to what that will then look like. So these are snapshots. This would be a snapshot at t equals 0, and then a snapshot 2 seconds later. If we wanted the raft view, what we would need to know for the raft view is we'd need to know the location of the raft. Say the raft is at x equals 1.5 meters. Then you just put in x equals 1.5, so you'd say y of 1.5 t, and that would equal a sine of 2 pi over lambda times 1.5 minus 2 pi times the frequency times the time. Then you just have a plot of y versus t, which might look something like this. It depends on at t equals 0 what value this has. And so you'd see how the raft goes up and down at a particular time. And that would be a raft at 1.5 meters compared with a raft at 2 meters or a raft at 0. And so this is a mathematical expression for a particular kind of wave, the easiest one, a sinusoidal wave, and that would be for a wave traveling to the right with a speed given by this expression. If you want to look at a wave traveling to the right, a wave traveling to the left, so wave traveling left, it turns out that the expression is exactly the same. We just change the sign. Plus 2 pi frequency times time. So this is a wave traveling to the right, traveling wave, and this is a wave traveling to the left. And in both cases, the wave speed is given by this same expression that we've used before. So this gives us a mathematical expression of the wave. The wave speed is given by, in a string, for example, or rope that's under tension. So typically we do it by taking a string like this and having it often with a weight down here. In practical terms, we put a pulley there and a weight so that we have a tension on this string, and then we maybe oscillate it up and down like this, which sends a wave down this string, and so we can record that wave at any particular time with the snapshot, or the raft might tell us what's going on, say, at that middle point, if we like. So a wave on a string, we can change the speed of the wave is given by, it turns out that it's given by the tension that the string is under over the mass per unit length. This mu is a mass density, mass per length, tells us the wave speed. So once you've got a string set up, the speed is fixed. It's fixed by the material. How heavy is the material, mass per length, and how much tension, how tight is that. And in general, wave speeds are given by, on average, they're given by something that tells us about, we can write it like elasticity, elastic, over sort of inertia effect. And what this means is that the elastic is really sort of a measure of how quickly it returns to its usual shape, so returns back to original location, sort of how springy it is and how quickly it comes back to the original location. And the inertia, how heavy something is, tells it, is a measure of how hard it is to get something to change its speed. So this is, you can think of this as reluctance to change speed. So when we have waves that are going through different materials, whether it's going through a string where the force of tension determines on how elastic, how quickly the string goes back, snaps back to its original position compared to its mass. When we're looking at sound, it has to do, for sound, we depend on this elasticity here. Depends on how sound through air, depends on how compressible the air is, a gas, versus the inertia associated with the molecules in the gas. So you can, as your mass goes up of your gas, for an ideal gas, then your speed goes down. And then in solids, it also depends on something called the bulk modulus that has to do with its compressibility, really. So all of these things tell us about the speed of a wave in the medium. And hopefully that makes sense, that it depends on how quickly something springs back and how heavy it is, how hard it is to change the speed. And so for air, we just have a speed of sound in air. So sound in air is around 340, as you saw, meters per second. And you can actually derive that using the ideal gas law and get sort of a measure of what approximately you predict the speed of sound in air is, and you're not too far off on this. This does depend on temperature, right? Because your density is going to depend on temperature.